Hello YouTube. So in this video, I'm going to present an alternative to the L'Hopital's rule that I'm sure all calculus students know pretty well, and that is the Stolz-Cesàro lemma. And so the Stolz-Cesàro lemma pretty much covers the same cases that the L'Hopital's rule can be applied to, but it's a bit more convenient in certain limits, which I demonstrated in one of my previous YouTube videos, so go check that out. It's in the description. And the lemma consists of two mathematically equivalent statements, and I'll be covering statement 1. So let A of n and B of n be two sequences in the real numbers. So I'll be using this notation. It's a bit sloppy, but you'll understand what I'm saying. So then the following three conditions must be true. So first of all, B of n is monotone. So monotone just implies that it's either strictly increasing or strictly decreasing. B of n must also be divergent. So if B of n is divergent and monotone, then logically speaking, it must be the case that B of n is either strictly increasing towards positive infinity or strictly decreasing towards negative infinity. One of the two must be true. And the third condition is the most important, that is that the limit as n goes to infinity of A of n plus 1 minus A of n divided by B of n plus 1 minus B of n is equal to L1, which is a finite number. And so L1, as long as this limit is finite, then you have the green light to do what is next, which is that if you have these three conditions, then it follows that the ratio of the two sequences, the limit as n goes to infinity of that ratio actually converges to that same L1 that we have up here. So that's pretty neat. So let me just box that right here for you to admire. And that is for the case where B of n diverges to some form of infinity. And note that there's no restriction on A of n. So A of n can do whatever the heck you want. It could converge, it could diverge, doesn't matter. All we need to know is that B of n is monotone divergent, and this is true. All right, so we have that out of the way. Now I want to move on to statement 2, which is for the 0 over 0 case. So let me define C of n and D of n, and these are similarly in the real numbers, okay? They're sequences of real numbers. Now, the following must be true. So first of all, D of n must be monotone decreasing. Okay, it's monotone decreasing, and we must also have that C of n and D of n approach 0 as n goes to infinity. And then the final statement, the more important one, same as the last time, it's that the limit as n goes to infinity of C of n plus 1 minus C of n divided by D of n plus 1 minus D of n is equal to some limit, some finite limit, which I'll call L2. And if that is true, then the ratio of the limits C of n divided by D of n must be the same limit, L2. And let me box that for you. All right, have a look, admire the theorem. Then I'll be covering some possible use cases and examples in the second part of the video. All right, here's our first use case. So let the sequence L of x of n be a sequence of real numbers, and it converges to L, which is finite. Then prove that the limit as n goes to infinity of the nth root of the product of all x's is equal to the limit as n goes to infinity of x of n. So that's quite a mouthful. Could take a few seconds to process that. Now, where do we get started? Because this is kind of, tricky a little bit. Well, I'll show you. So define two sequences A of n, and this A of n will be defined as the logarithm of the product of all x's. So x1, x2, so on to xn. Okay, and then we'll define b of n, the sequence, to just be n. Now, as you can probably tell, I'm going to be using statement 1 of the Stolz-Cesàro lemma, where b of n diverges. So, first of all, statement 1, what does statement 1 say? Well, statement 1 requires, first of all, that 1, b of n is divergent monotone. I'll just abbreviate it, so I'll just shove divergent monotone in the same statement. And then we must also have that limit of a of n plus 1 minus a of n divided by b of n plus 1 minus b of n. That approaches some finite number. I won't call it L, but it's equal to some mystery man that is finite. So if it's equal to some mystery man that is finite, then that implies that limit as n goes to infinity of the ratios is also that same mystery man number that's finite. Okay, so we have the first statement we have the first condition satisfied. Now we just need to find this number. And then once we find this number, we can find this, and this might be particularly helpful in the future. So, okay, so let's just get started then. So, limit as n goes to infinity of a of n plus 1 minus a of n divided by b of n plus 1 minus b of n. Yeah, my handwriting's severely deprecated, but it's okay. I'm sure you can understand what I'm saying, I hope. So, we can just plug and chug here. So we have logarithm, and then I'll just use the pi symbol to notate products. If you've been in sufficiently advanced math, then you must have seen this. Okay, so that brings us to here. And then there's multiple ways to simplify this. First of all, the ends can just cancel out, leaving us with just 1 in the denominator. But you may remember that from algebra, that if you take the logarithm, the difference between two logarithms, provided that a and b are positive real numbers, you get logarithm of a divided by b. So subtraction becomes division inside the logarithm. So we can apply that same thing here, because we know that if we divide this product with this product, every single term up to x of n will be canceled out. And that leaves us with only x of n plus 1 being uncancelled. So that leaves us with logarithm of, well, actually rather the limit as n goes to infinity of the logarithm of x of n plus 1. And since we know that x of n is a convergent sequence, then if you just bump the index forward by 1, well, that bumped index sequence must converge to the same limit as well. So this will just become logarithm of L. Note that the operation logarithm and limit can commute because logarithm is continuous. I think that's the reason. If I'm wrong, please correct me. So we have logarithm of L. Fine. Well, where does that bring us? Well, we know that this ratio here approaches a finite limit. So then it follows that by the Stolz-Cesàro lemma that limit of the ratios of the sequences must also approach logarithm of L. Okay, so now that we have this very useful fact, let me just erase all of this work because it's no longer necessary. Okay, what is a of n again? Well, a of n was defined as what? The logarithm of the product of all x's. Okay, and then divided by n, because b of n is just n. And we know that this is equal to log of L. Now, if you remember from one more fact from algebra, that if you have logarithm of x to the a power, that's equal to a times logarithm of x. So how is that remotely helpful in this case? Well, we can say that that coefficient on the outside is 1 over n. So we can set logarithm of x1, x2, so on, over n. Well, first of all, let me write this as 1 over n. This is mathematically equivalent to x1, x2, and then so on to x of n to the 1 over n power. They're algebraically equivalent, and the thing is, this must be equal to logarithm. This must approach logarithm of L, since they're the same thing. And if that is the case, well, then since logarithms are continuous, you can just raise both sides to the power of e. Or sorry, you could raise e to the power of both sides. So then you would get that you have x1, x2, so on to xn, raised to the 1 over n power approaches L. You're just canceling out the logarithms on both sides, which is possible. And, well, is that not what we have here? Mathematically equivalent way of, or I keep saying that. This can just be restated as the nth root of the product of all x's is equal to L, which is actually just our limit. So yeah, we have limit as n goes to infinity of x of n. All right, so for our second use case, which is an extension of the first use case, we have the sequence y of n, which is a sequence of positive real numbers indicated by this notation. Now we want to prove that the limit as n goes to infinity of the nth root of y of n is equal to this expression over here, the limit as n goes to infinity of the ratio of consecutive terms times the nth root of the initial condition y of 0. Okay, so how do we get started with this? Well, first of all, let's define a separate sequence x of n to be y of n divided by y of n minus 1. Okay? Then it follows that the nth root of x1 all the way, product x2 all the way to xn, well, what is that? That is the nth root of a lot of quotients. So we have one corresponding to this, so y1 divided by y0, y2, y1, all the way to y of n divided by y of n minus 1. Okay, so, well, how do we proceed from here? Well, we have this cancels out, this cancels out. All the diagonals cancel out, leaving us just with the nth root of y of n divided by y of 0. So you can see we're kind of getting somewhere close, but we're not quite there yet. Now we know that the limit as n goes to infinity of this guy over here, nth root x1, xn, is actually just equal to the limit of, well, yn of n minus 1, because this is equal to the limit of x of n, and x of n is defined as such. So now this limit is also equivalent to this over here. So we have limit as n goes to infinity of the nth root of y of n divided by y of 0. So, well, where does that lead us? Well, we can multiply both sides by the nth root of y0. So let me just erase this on the top here. Erase this too. So then this is, well, equivalent to y of n minus 1 times the nth root of y of 0 is equal to the limit as n goes to infinity of nth root of y of n. And so that thus proves, well, our theorem up here. So as promised, I'll provide a very simple example. So what is the limit as n goes to infinity of the nth root of n. So we'll need to define a y of n, so I'll define y of n as simply n, because that's what's in the root. And we also need to define an initial condition y of 0, so we pick whatever is convenient. Now, the reason why we can do that is because we know that the natural numbers, a sequence first of all, well, what is a sequence? A sequence, say x of n, is actually a mapping from the natural numbers to the reals, at least the sequences that we're talking about. And the natural numbers consists of, the set 1, 2, all the way to, well, wherever. So it does not include 0. So there is technically no y of 0 term actually defined. So we can just define it as whatever we want to be. And in this case, 1 is convenient, so we define it as 1. So therefore, the sequence y of n only consists of positive real numbers. So then we can just use the formula that we proved earlier, which is that the nth root of n, where y of n is n, is simply just the limit as n goes to infinity of, well, y of n plus 1 divided by y of n. What is that? Well, that's n plus 1 divided by y of n. And then we can take the nth root of y of 0, but that's just 1, so I'm not going to even involve it in here. That's just 1.